Welcome everyone, thank you for being here today. We will be talking about reinforcement learning, state action values, and actual examples. In more detail, we will be talking about inaccuracy of state action value function for non-optimal actions in adversarially trained deep neural policies. I would like to start with reinforcement learning. So you can see we have a markov decision process represented as a tuple here. We have an agent interacting with an environment, observing states, taking actions, receiving some rewards, and exploring and trying to find an optimal policy which will give maximum expected cumulative discounted rewards. And here in this MDP tuple, we have S finite set of states, a finite set of action, P Markovian transition kernel, which is basically gives us in state S by taking action E, what's the probability that we're going to end up in state S prime. We have reward function, which basically gives us in state S, if we execute action A, what will be the rewards we get. We have discount factor gamma, which is penalizing the future rewards compared to the rewards we might get from the current state by executing action A. And we have rho 0, the initial state distribution. So the goal here is basically to learn for each state action pair a value, and learn in state S, if I pick action A, what will be the expected cumulative discounted rewards that I will receive. And this is achieved by iterative Bauman update. And the goal is to learn the state action value function for each state action pair. We have also value function representing the value of the state, which is equal to the maximum of the state action value in state S, and we have optimal policy. Pi star is executed by picking the action, maximizing the state action value in state S. And as you can see, this value for each state action pair can be stored in a tabular form. However, if we have a large action or state space, that might not be true anymore, and we might need to approximate this state action values. And as we all know, deep neural networks have been applied to do this approximation, and deep reinforcement learning has been applied in many domains, from autonomous driving, financial trading, and drug design. But there are still some concerns related to the robustness and the resilience of the deep neural policies. And we will be talking about that part today. I would like to move forward to adversarial perturbations in reinforcement learning. And initial work is based on applying fast gradient sign method perturbations in reinforcement learning, and some work focusing on timing perspective. And Paternik et al. Proposes to increase the probability of taking the worst possible action in a given state. And worst possible action here is the action minimizing the state action value in state S. And Glave et al. Proposes to model this adversary more like an adversary can take natural actions in a given environment rather than alpino-bound perturbations. And while there is several work on this adversarial perturbation, another line of work focuses on how we can make our policies more robust to these perturbations. And the initial work on this is adding this FGM perturbations in the training data proposed by Melkar, and Pinto et al. And Glave et al. Proposes to model as a zero-sum game. And Glave et al. Here again has a different definition for an adversary who is allowed to take natural actions in a given environment instead of the alpino-bound perturbations. And quite recently, Juan et al. Proposed a state adversarial MDP to model. And in this paper, authors claim that their proposal obtains theoretically justified robust policies. And we will be talking about this work. So you can see here a state adversarial Markov decision process, SAMDP, looks quite similar to the first slide we discussed, except with a quite small modification that we have an adversary can modify the observations of an agent. While the adversary can modify the observations of an agent, the rest of the dynamics of the environment is still the same. The meaning is that the agent will still receive the rewards of the unperturbed state. And authors in this work propose state adversarial double deep Q network, which is basically this regularization term that you see in equation 5 is added to the temporal difference loss in Q learning. And if you look at closely, what is this regularization term is basically the state action value of the adversarial state with the action which is not equal to the action maximizing the state action value in unperturbed state minus the state action value of the adversarial state with the action maximizing the state action value of the unperturbed state. And as you can see, this regularization term will be minus if the action taken in unperturbed state versus the perturbed state is equal to each other, and it's going to be positive if agent changes the action taken due to the perturbation compared to the unperturbed state. And you can see here the adversarial state is inside the L infinity norm bounded by epsilon. And let's move forward to what we did in our work. And in here you can see the layout of action modification. So what we are going to do is to make the agent pick the second best action with probability P and make the agent pick the optimal action with probability 1 minus P. Optimal action here is the action maximizing the state action value in state S. Let's move forward to our experimental results. So you can see here the results for Roadrunner and Bandgeist. We plot the performance drop with respect to the probability P. And you can see there's a clear gap between the adversarially trained deep neural policies and vanilla trained deep neural policies. It's important to know here that this is a graph of performance drop. So you can see here that the vanilla trained deep neural policies are more robust towards these action modifications compared to adversarially trained deep neural policies. However, more importantly, this result shows us that the state-of-the-art adversarially trained deep neural policies do not have an accurate representation for non-optimal actions. And in our paper, we hypothesize that this might cause overestimation of state action values, and we argue that the root cause of this problem might, based on applying existing adversarial techniques proposed for image classification and deploying them in reinforcement learning setup. Because the state action value function in reinforcement learning has a meaning for each possible action, meaning that by taking action A, the state action value function tells us what will be the expected discounted cumulative rewards we will receive, and compared to just executing the correct label or optimal action in each state. And we think that the future work focusing on adversarial training might consider the reinforcement learning problem in adversarial training. Thank you for listening.